Welcome to our Galactic Observatory. Tonight, we enter America's deadly multi-hazard tornado outbreak happening right now. A single continental collision zone lets one sprawling system unleash tornadoes, floods, ice blizzards, and heat. Above it all, a carved jet stream trough accelerates the outbreak and arranges the atmosphere. Below a deepening surface, low drags cold, warm, and dry boundaries into dangerous alignment tonight. From the Gulf, warm moisture surges northward, feeding the storm field with invisible combustible breath. Inside the warm sector, buoyant air stores violence beneath cooler air, building instability across the plains. Then wind shear bends with height, turning hidden horizontal spin into organized rotating structure aloft. When fronts and dry lines finally lift through it, stored energy erupts into towering storms. After dark, the same tornado becomes deadlier because darkness erases sight context and reaction time. Soon, storms merge into squall lines, where embedded mesovortices can still spin tornadoes through rain. Inside those cores, violent updrafts forge giant hail, while downdrafts drive devastating straight-line winds outward. Taken together, these repeating compound outbreaks raise harder climate questions, even where certainty remains incomplete. Like, subscribe, and thank you for listening. Now the first collision begins above North America. Across one immense sky opposite, seasons collide and separate. Disasters begin breathing from the same engine. That sky-level architecture presses downward, sharpening invisible lanes where surface boundaries can suddenly matter most. For a moment, the cap holds, and the charged atmosphere waits like a locked spring. Some storms stay isolated, and those discrete supercells preserve focus rotation and exceptional destructive freedom. Near the ground, tightening rotation beneath the supercell condenses from hidden motion into tornado form. And as the system widens, its single engine begins delivering radically different dangers at once. On the warm side come floods, while the cold side hardens into ice and blizzards, where people sleep and infrastructure strains. Warning lead time collides with exposure, distance, and timing. Across the broad central span of North America, the atmosphere arranges itself into a pattern that looks ordinary on a map at first glance, and then grows more unusual the longer it is examined. Air is always moving across this continent. Pressure systems rise and fall. Warm air moves north, cold air moves south, and storms form where those different air masses meet. In a severe outbreak, the difference is not the existence of those ingredients, but their scale, their timing, and the sharpness of their contrast. Over the course of this event, the continent holds several seasons at once. Far to the south and east, warm and moisture-rich air spreads over the land in a broad sheet drawn inland from the Gulf and held close to the ground. Far to the north and west, colder and drier air advances behind a powerful system carrying the character of late winter, even as the calendar has already moved deeper into spring. Between those two large realms, the atmosphere does not settle into a gentle transition. It compresses, it tightens, it creates a corridor where temperature, moisture, and wind change rapidly across surprisingly short distances. That corridor becomes the stage on which many kinds of dangerous weather can exist at the same time. This is the first fact that gives the outbreak its unusual character. It is not a single storm in the narrow sense. It is a continental-scale collision zone broad enough to contain tornadoes in one sector, flash flooding in another, freezing rain farther north, and blizzard conditions beyond that. Each hazard appears different at the ground, and each demands a different human response, yet they are all tied to one atmospheric arrangement. The system is large enough that its warm side feels almost summer-like in places, while its cold side still carries the structure and discipline of winter. The boundary between them is not a thin line drawn neatly across a weather map. It is a wide and restless region of conflict, with pockets of unstable warmth zones, of lifting air and channels of fast motion overhead that help organize the whole structure. In practical terms, this means that a person in one city can be dealing with rising water in streets, while another several hundred miles away, but still under the influence of the same system, is watching ice collect on trees and power lines. Farther south, someone else may be listening for thunder, and farther north, visibility may be collapsing in wind-driven snow. The atmosphere is not choosing one mode of danger. It is sustaining several modes at once, because the continent beneath it is wide enough, and the contrast within the air mass is strong enough to support all of them together. This is why such outbreaks feel overwhelming when described in a single sentence. The hazards seem unrelated until the larger structure is considered. Once the larger structure is visible, the logic becomes clear. Warm air flowing northward near the surface creates one set of conditions. Cold air pressing in from the west and north creates another. Moisture adds weight and energy to the lower atmosphere. Dry air in nearby regions sharpens boundaries and helps define where storms can ignite. The turning of the earth, the shape of the land, the orientation of the air masses, and the seasonal position of the continent under shifting spring sunlight all contribute to the arrangement. None of these factors alone is enough to create the full outbreak. Together, they produce a broad tension field across the nation. The central United States is especially vulnerable to this kind of setup because it allows air from very different source regions to meet with little obstruction. Warm, humid air can move north from low latitudes. Cold continental air can surge south. Dry, elevated air can arrive from the interior west. The landscape does not block these exchanges very much. Instead, it allows them to spread overlap and sharpen into gradients. A gradient is simply a place where one atmospheric property changes over distance. During ordinary weather, gradients may be modest. During an outbreak like this one, they become extreme. Temperature can shift quickly over a day's drive. Moisture can fall off sharply across a boundary. Wind can change both speed and direction from one side of the system to the other. Those changes do not merely describe the weather. They create it. They define where clouds deepen, where precipitation changes form, where pressure falls, and where energy gathers in the lower atmosphere. From the widest perspective, the continent begins to resemble a basin filled with moving layers. Some layers are warm and buoyant. Some are cold and dense. Some are wet. Some are dry. And some are moving much faster than others. Where they overlap in the wrong combination, the atmosphere becomes unsettled. Where they are forced together over great distances. At the same time, the result is not local instability, but regional upheaval. The same large arrangement that permits severe thunderstorms in the central warm sector also ensures that areas to the north remain cold enough for ice accretion or snow, while zones to the east and southeast may be wet enough for flooding rains. This is not weather behaving randomly. It is weather expressing the full range of possibilities contained within one very large structure. The outbreak becomes deadly not only because individual hazards are intense, but because the system occupies so much of the continent that it strains forecasting travel infrastructure and attention all at once. Roads, power lines, drainage systems, and warning networks are each tested in different ways, depending on location, but all under the same parent circulation. The human impression is one of chaos. The atmospheric reality is one of order at a very large scale, with that order producing different forms of danger in different sectors. Seen from high above, the event is not yet a tornado, not yet a flash flood, not yet a sheet of ice on branches. It is first a continental arrangement of opposing air masses, locked together in motion, carrying enough contrast and enough reach to place winter and summer inside the same system, and hold them there long enough for the land below to feel both. Above the visible weather, above the clouds and the rain shields, and the sharp line where warm air meets cold, the deeper structure of the outbreak takes shape in the fast-moving air of the upper atmosphere. This is where the event gains organization. At the ground, weather can look scattered and complicated with separate storms and changing hazards in different states. Higher above, the pattern becomes more unified. A large trough in the jet stream bends across the continent, and that bend matters because the jet stream is not simply a band of wind. It is a steering current, a source of momentum and a framework that helps determine where air rises, where it sinks, and where surface pressure tends to fall. When the flow aloft grows stronger and more curved, the atmosphere below becomes more responsive. The outbreak begins to behave less like a collection of local accidents and more like a coordinated system. In this case, the jet stream is not flat and unremarkable. It is amplified, meaning the usual west to east flow develops a pronounced wave. One segment dips southward, and that dip allows colder air from higher latitudes to press farther into the interior of the country. Ahead of that dip, the air aloft accelerates and spreads. This combination is important because a trough is not merely a shape drawn on a chart. It is a dynamic zone where temperature contrasts and wind speed contrasts intensify. Air parcels entering one side of the trough can be stretched, turned, and redistributed. The result at lower levels is often a broad encouragement for rising motion. Rising motion does not guarantee severe weather by itself, but it prepares the background state in which severe weather can become more likely. The upper atmosphere, in effect, starts clearing the way. The term negatively tilted is often used when a trough takes on an especially dangerous orientation for severe storms. In plain terms, this means the axis of the trough leans from northwest to southeast, rather than standing more upright from north to south. That angled structure often signals a mature and strengthening system. It tends to increase the overlap between strong winds aloft and the warm, unstable air at lower levels. When those ingredients overlap, storms become easier to organize and harder to disrupt. The air is not merely rising. It is rising in an environment where the winds above it are fast enough to ventilate developing storms, removing air from their tops and allowing fresh, warm air to keep feeding upward from below. This is one of the quiet but critical roles of the jet stream. A storm that cannot shed air aloft struggles to maintain itself. A storm that can exhaust efficiently into strong upper-level flow is able to deepen and persist. The upper atmosphere therefore acts almost like a hidden support structure, invisible to anyone on the ground, but essential to the life cycle of the outbreak. Wind speed at these levels can exceed 100 miles per hour, and that speed matters not because it is directly felt at the surface, but because it changes the vertical profile of the atmosphere. It creates shear, the variation of wind with height that later becomes central to storm rotation. Even before rotation is considered in detail, the basic fact is enough. The faster and more differently directed the winds become with altitude, the more potential there is for storms to take on lasting structure rather than collapsing into short-lived cells. The jet stream also separates air masses of different temperatures, and where those temperature contrasts sharpen the atmosphere, stores more available energy for motion and reorganization. The upper pattern is therefore both guide and engine. It guides the surface low along a favored path, and it helps energize the entire column of air from top to bottom. Another important feature of the upper-level architecture is divergence, the spreading apart of air in certain zones aloft. When air spreads apart high in the atmosphere, the mass of air above a region is reduced. Surface pressure can then fall in response, and falling pressure encourages inward motion at lower levels. That inward motion helps gather warm, moist air into the system. In this way, the upper atmosphere does not stand separate from surface weather. It reaches downward through pressure changes and broad vertical motion, helping the surface cyclone intensify and the frontal boundaries sharpen. The strengthening of the outbreak is therefore not only a matter of warm air arriving near the ground. It is also a matter of support from above becoming more efficient and more forceful. The wave in the jet stream is like a long overhead lever, and as it deepens, it lifts and rearranges the atmosphere beneath it. This is why meteorologists watch the upper pattern with such care. A storm system at the surface may still look manageable when the upper support is modest. Once the upper flow intensifies and aligns properly, the same surface ingredients can produce much greater consequences. The timing of that alignment often determines whether a setup remains only moderately active or becomes a major outbreak. Across the broad central and eastern United States, the upper winds during such an event are not uniform. Some regions lie beneath rising branches of the flow where storms are encouraged. Others lie beneath subsiding branches where air sinks and clouds may briefly thin. These contrasts create corridors of greatest concern. The most dangerous zone is often where strong lift aloft overlaps with rich, low-level moisture and favorable wind profiles. The jet stream cannot produce tornadoes directly, and it cannot flood a road by itself. What it can do is build the environment in which all of those things become more probable. It bends the large-scale flow, intensifies the pressure pattern, increases wind shear, and helps sustain vertical motions over a large area. Once that framework is in place, the lower atmosphere has far less freedom to remain calm. The outbreak becomes, in a sense, architected from above. Seen from this perspective, the violent weather below is not yet a matter of individual storms or local warnings. It is first the consequence of an increasingly powerful sky structure, an overhead current shaping the continent's weather like a hidden set of hands, guiding motion, sharpening contrasts, and building the dynamic scaffold on which the rest of the event will stand. At the surface, the broad architecture of the outbreak becomes visible in a more familiar form, not as invisible rivers of fast air high above, but as pressure centers and boundaries moving across the land. This is the level where maps show a low-pressure center, warm and cold fronts, and in some cases a dry line. These features are often presented as simple symbols, curved lines with triangles or semicircles, but on the ground, they are not thin marks. They are wide transition zones, sometimes subtle and sometimes abrupt, where the air changes character over space. The surface cyclone, or low-pressure system, is the organizing center of this arrangement. Air flows inward toward lower pressure, and because the Earth rotates, that inward flow also curves. The result is a circulation that gathers air from different source regions and places them into contact. Warm air is drawn northward and eastward on one side. Cold air wraps in from the west and north on the other. The low is not merely a passive marker of stormy weather. It is an active mechanism that concentrates contrast and motion into one evolving structure. As the low deepens, the pressure difference across the region increases, and stronger pressure differences usually mean stronger winds. Those winds matter at the ground because they transport moisture, sharpen temperature contrasts, and help define where lift will occur. The cold front extends away from the low as the leading edge of denser advancing air. Cold air is heavier than warm air, so when the two meet, the colder air tends to wedge underneath. This forces the warmer air above it to rise. Rising air cools clouds form, and precipitation or thunderstorms can develop if the atmosphere is moist and unstable enough. The warm front behaves differently. Here, warmer air advances over cooler air already in place. Because the warm air is lighter, it often glides upward more gradually over the retreating cool air. This tends to create broader cloud shields and stratified precipitation. Though under the right circumstances, the warm frontal zone can also become a focus for strong rotation because it sharpens temperature and wind contrasts near the surface. Then there is the dry line, one of the most distinctive boundaries in severe weather patterns across the central United States. Unlike a cold front or warm front, the dry line is defined less by temperature and more by moisture. On one side, air is warm and dry, often with roots in the elevated terrain of the interior West. On the other side, air is warm and moist, often supplied from the Gulf. That difference in moisture changes density and cloud potential. Dry air can mix deeply during the day, while moist air near the ground retains more latent energy, meaning energy tied to water vapor that can later be released as air rises and water condenses. Where those two air masses meet, the contrast can become sharp enough to force air upward, especially during the afternoon when solar heating is strongest. In a major outbreak, these boundaries do not exist in isolation. The surface, low, the cold front, the warm front, and the dry line all interact, and their geometry determines where the greatest danger develops. One reason this matters so much is that boundaries are not only places of lift, they are also places where winds change direction over short distances. That directional change increases the potential for rotation in storms that form nearby. A storm developing along an open, featureless area of unstable air may still become severe, but a storm rooted near a boundary has access to enhanced structure. The boundary becomes both launch point and modifier. In some regions, the air on one side of a front is only modestly different from the air on the other. In an outbreak like this one, the differences can be dramatic. Temperatures may vary sharply, dew points may shift noticeably, and wind may veer or back over relatively short distances. Those shifts create small local zones where conditions become more favorable than the broader region alone would suggest. A map can therefore show a large threat area, but within that area, the true hotspots often lie near particular segments of these boundaries. The motion of the boundaries also matters. A cold front advancing too quickly can undercut storms and push them into a more linear mode, encouraging a squall line rather than long-lived isolated supercells. A warm front lifting northward can bring higher moisture and lower cloud bases into a region, making rotating storms more efficient at producing tornadoes. A dry line mixing eastward during the day can ignite the first storms of the afternoon, acting almost like the striking surface that releases energy stored for hours near the ground. The surface low ties all of this together by controlling the broader wind field. South and southeast of the low air tends to flow poleward from warmer source regions, carrying moisture inland. West of the low, colder and drier air pushes in. North of the low, cooler air can remain entrenched near the surface, setting the stage for freezing rain or snow if precipitation falls into that layer. This is why the same system can support severe thunderstorms in one state and winter hazards in another. The low is not generating all hazards equally everywhere. It is arranging the boundaries so that different hazards emerge in different sectors. In the warm sector between the warm front and cold front air is often richest in moisture and most capable of instability. Near and north of the warm front surface air may remain cooler, but wind profiles can become especially favorable for rotation. Along the cold front, forcing becomes stronger, and storms may merge into organized lines. Along the dry line, earlier, discrete storms may develop in the open, warm air. These differences matter because the outbreak is not just a matter of how much energy exists. It is a matter of where the boundaries place that energy, how they release it, and what storm form emerges in response. Surface maps, therefore, tell a story of motion and conflict. They show where one air mass is advancing, where another is retreating, and where the sharpest seams in the atmosphere are temporarily exposed. Those seams are where storms often find their first structure. The deeper into the outbreak one looks, the clearer it becomes that the boundaries are not background details. They are the frame of the event at ground level, the visible edges of contrasting air masses whose contact sets the terms for everything that follows. Once the surface boundaries are in place, the outbreak depends on something quieter but equally important, the long inland return of moisture. A severe weather pattern can have sharp fronts, strong upper winds, and a deep surface low, yet still fail to produce a major tornado outbreak if the lower atmosphere remains too dry. Moisture is the difference between a system that looks threatening on a map and one that can sustain deep rotating storms over a wide area. In the central and eastern United States, that moisture often comes from the Gulf. The movement is not dramatic to anyone standing outside. It does not arrive as a visible river. It comes as a gradual change in the feel of the air near the ground, the kind of change that makes the atmosphere seem heavier, softer, and less willing to cool after sunset. Dew point is one way meteorologists describe this moisture content. Higher dew points mean more water vapor is present in the air. When those values rise over a broad region, the lower atmosphere becomes more capable of feeding thunderstorms. Water vapor stores latent heat, which is energy held in an invisible form until condensation begins. When air rises and cools enough for clouds to form, that stored energy is released. The release adds buoyancy to the rising air and helps it continue upward. This is why moist air is not simply humid air in the everyday sense. In storm dynamics, it is fuel. The Gulf serves as a broad, warm reservoir that can supply this fuel over great distances. South winds ahead of the surface low pull that air northward, often for many hours or even several days, depending on the pattern. The quality of the outbreak depends not only on whether this transport happens, but on how deep the moist layer becomes and how far inland it can spread before mixing out or being interrupted by cooler air already in place. In the best severe weather setups, the return flow is persistent and well organized. Air near the ground streams northward through Texas, the lower Mississippi Valley, and the Central Plains or Midwest, carrying moisture beneath stronger winds aloft. This creates a layered atmosphere in which the surface becomes warm and humid, while the air above remains different enough to preserve instability. The moisture transport is strongest where the pressure pattern supports it. South and southeast winds feed directly into the warm sector, and because the air is moving over land that is warming during spring, the near-surface environment can become especially supportive of storm growth. Not every area within the warm sector receives the same quality of moisture. Local differences matter. Some places are affected by earlier storms that leave rain-cooled air behind. Some lie closer to a warm front, where shallow, cool air still lingers near the surface. Some experience stronger daytime mixing, which can dilute surface moisture by drawing drier air downward from aloft. These details influence where storms later become most intense. Still, the broad principle remains the same. Without a sustained northward stream of moist air, the outbreak loses one of its essential supports. The role of moisture is sometimes misunderstood because it does not act alone. High humidity does not automatically mean tornadoes. Instead, moisture interacts with lift temperature and wind structure. It lowers cloud bases by reducing the distance air must cool before condensation begins. Lower cloud bases can help storms connect more efficiently with the rotating air near the ground. Moisture also raises equivalent potential temperature, a way of describing the total heat content of an air parcel when both temperature and water vapor are considered. Higher values mean the parcel has greater potential to rise vigorously once it is lifted and begins condensing. This is one reason why rich, low-level moisture is so often present in major warm-season outbreaks. It deepens the pool of air that can participate in storm growth. In a multi-hazard system like this, one moisture also helps explain why different threats emerge in different places. In the warm sector, deep moisture supports thunderstorm development and heavy rainfall. Along slower-moving boundaries, or in areas where storms repeatedly pass over the same ground, that rainfall can accumulate quickly enough to overwhelm drainage systems and create flash flooding. Farther north, where cooler air remains entrenched near the surface, moisture lifted over that cooler layer can fall as freezing rain, sleet, or snow, depending on the temperature profile through the atmosphere. The same basic supply of water vapor can therefore end in very different forms at the ground. Its final outcome depends on what kind of air it moves through on the way down. Moisture return also has a timing dimension. During the night, the lowest part of the atmosphere often develops a stronger current, known as a low-level jet. This is a corridor of relatively fast wind a short distance above the surface. It can intensify the transport of warm, moist air after sunset, which is one reason nighttime severe weather can remain dangerous even after daytime heating fades. The surface may cool, but moisture can continue arriving above it, and storms can remain fed by that inflow. In some setups, the low-level jet strengthens precisely as storms organize into lines or move into more densely populated areas. That timing is especially dangerous because it allows the outbreak to persist into the hours when people are least aware. The movement of Gulf moisture inland is therefore not a background detail, but a central conveyor of energy. It makes the warm sector feel different, changes the depth of instability, lowers cloud bases, supports heavy rain, and helps maintain storms after dark. It also links the continental scale pattern to local experience. The person standing outside ahead of the storms notices sticky air and a persistent breeze from the south. Those modest sensations are the surface expression of a much larger transport process already underway. The atmosphere is quietly loading itself. The moisture is not the storm not yet, but it is what allows the storm to become more than a brief tower of cloud. It is the hidden richness of the lower atmosphere steadily drawn northward, filling the warm sector with energy that remains invisible until lift begins and the sky finally responds. Within the warm sector, after moisture has returned and spread through the lower atmosphere, the next important condition is instability. This word sounds abstract, but in weather, It refers to something very physical. It describes an atmosphere in which air near the surface is able to rise and keep rising once it is lifted. That continued ascent matters because thunderstorms are built from vertical motion. Without sustained upward motion, clouds remain shallow, rain stays light, and the atmosphere releases its energy slowly. With strong instability, rising air accelerates, towers deepen rapidly, and storms can grow tall enough to reach the layers of stronger wind and colder temperatures where severe weather begins to take form. Instability is therefore the warm sector's stored potential. It is the energy waiting in the lower atmosphere before the first explosive storm fully develops. The structure is often simple in principle. Near the ground, the air is warm and moist. Above it, the air is cooler and often drier. Warm air is less dense than cold air, so if a parcel of surface air is nudged upward and remains warmer than the air around it, it continues to rise on its own. As it rises, pressure decreases, so the parcel expands and cools. At first, it may cool faster than the surrounding air, especially if it is still unsaturated. But once it cools enough for water vapor to condense into cloud droplets, latent heat is released. That released heat slows the parcel's rate of cooling and can help it remain warmer than its surroundings. If that advantage is large enough, the parcel becomes buoyant and accelerates upward. The atmosphere then behaves like a system that has been holding a compressed spring. Once released, the spring does not relax gently. It pushes hard. Meteorologists often measure this stored upward potential with a quantity called convective available potential energy. In practical terms, it is a measure of how much positive buoyant energy an air parcel can access if it rises through the favorable part of the atmosphere. Larger values do not guarantee a tornado or even a severe storm, but they do indicate that the atmosphere is capable of supporting stronger updrafts if other ingredients cooperate. A strong updraft is important because it can lift water and ice high into the storm-sustained large hail growth and create the deep rotating structures associated with supercells. In the warm sector of a major outbreak, instability is rarely uniform. One county may hold richer moisture and stronger heating than the next. One corridor may have been shaded by morning cloud cover, while another cleared early and warmed more efficiently. These differences matter because solar heating changes the temperature of the air near the ground, which changes how buoyant that air becomes. A warm, humid afternoon beneath cooler air aloft is often the classic pattern for rapid destabilization. Sunlight warms the surface warms the air just above it, and the contrast between that warmed low-level air and the colder air above grows larger. The larger the contrast, the stronger the potential upward acceleration once lifting begins. Yet the atmosphere often does not release this energy immediately. Between the warm surface air and the freer rising motion above, there may be a cap, a layer of warmer air aloft that suppresses early storm development. This cap can be helpful in severe weather setups because it prevents weak storms from forming too soon and consuming the energy in scattered, inefficient ways. As long as the cap holds warm, moist air continues collecting below it, and instability increases. If the cap breaks later in the day near a strong boundary, the first storms to form may tap into a much richer environment than they would have earlier. This is one reason some outbreaks escalate suddenly after hours of quiet conditions. The atmosphere spends much of the day storing energy, then releases it in a relatively short window. In a broad outbreak, instability also explains why the warm sector feels so different from areas only a few hundred miles away. north of a front cooler stable air may keep surface parcels from rising freely. West of a dry line, drier air may limit cloud depth or alter the balance of heating and moisture. But inside the favored warm sector, especially where moisture is deep and temperatures rise into the upper part of the seasonal range, the lower atmosphere becomes primed. It is not yet violent in visible form, but it is capable of becoming violent quickly. The sky may still look partly calm. Wind may blow steadily from the south. Low clouds may thin. Sunlight may return. None of these signs alone reveals the amount of stored energy. That is why instability can be deceptive. It is not noise or motion at the surface. It is readiness. The role of instability in this outbreak extends beyond tornadoes. A highly unstable atmosphere also supports intense rainfall rates, because strong updrafts can lift great amounts of moisture rapidly and condense it efficiently. It supports large hail because powerful upward motion can keep growing ice suspended long enough to become large before it falls. It supports lightning because vigorous vertical mixing helps separate electric charge within the storm. It even contributes indirectly to damaging straight-line winds, because strong storms can later produce heavy downdrafts as rain-cooled air descends. In this sense, instability is not tied to one hazard. It is the general intensifier of the warm sector. The particular hazard that emerges depends on what other ingredients are present alongside it. In the context of this outbreak, instability is especially important because it overlaps with sharp boundaries and strengthening winds through the depth of the atmosphere. That overlap means the stored energy is not isolated. It is positioned where storms can access it efficiently and then organize rather than collapse. The warm sector becomes more than a warm place. It becomes a reservoir of upward motion waiting for release. By late afternoon or evening, once the cap weakens or lift strengthens enough to overcome it, the atmosphere can transition from quiet heaviness to explosive growth in a short span of time. The instability had been there already invisible and accumulating, hidden in the contrast between surface warmth and upper-level coolness. When the release comes, it is only the visible expression of an imbalance that had been deepening for hours across the broad, humid air of the warm sector. Once instability is present, the atmosphere has the energy to build deep storms, but energy alone is not enough to explain why some thunderstorms become organized, long-lived, and capable of rotation. For that, the next ingredient is wind shear. Wind shear simply means that wind changes with height, either in speed in direction or in both. Near the ground, wind may blow from one direction at a modest pace. A few thousand feet higher, it may blow from a different direction and move much faster. Farther aloft, the speed may increase again. These vertical changes matter because a rising column of air does not move through a uniform environment. It rises through layers that are already sliding past one another. That layered motion creates the raw rotation that storms can later use. The atmosphere in a severe weather setup is therefore not only buoyant, it is also mechanically structured in a way that favors turning. A helpful way to understand this is to imagine a long, invisible tube of air lying nearly horizontal near the lower part of the atmosphere. This tube is spinning because the wind near the ground is slower or differently directed than the wind above it. The tube is not a tornado. It is not even upright. It is simply a region of horizontal vorticity, which is a formal term for local spin in the air. Such spin is common wherever winds change with height. In ordinary conditions, it may never matter much. In a strongly unstable environment, however, An updraft can intercept that horizontal spin and tilt part of it upward. Once tilted, the rotation is no longer lying flat. It becomes vertical, or at least partly vertical within the storm. This is one of the key mechanical steps in the evolution of a rotating thunderstorm. The storm does not create all of its rotation from nothing. It reorganizes spin that already exists in the environment. Wind shear therefore acts like a hidden reservoir of rotational possibility. The stronger and more favorably arranged the shear, the greater the chance that a storm can tilt and stretch that spin into a persistent rotating updraft. Speed shear and directional shear each contribute differently. If winds simply increase with height but remain from the same direction, storms can still become organized, because the stronger winds aloft help separate rising and falling air. That separation matters because a storm weakens when its rain-cooled downdraft falls back into the same area as its warm inflow. Shear helps displace the downdraft away from the updraft, allowing the storm to keep feeding on warm, moist air. Directional shear adds another layer. When winds turn with height, especially when low-level winds come from the southeast or south, and winds aloft come from the southwest or west, the lower atmosphere contains more horizontal spin that can be tilted into vertical rotation. This turning profile is especially favorable for supercells, which are thunderstorms with a deep, persistent rotating updraft called a mesocyclone. The mesocyclone is not yet a tornado, but it is one of the clearest signs that the storm has become dynamically organized. The storm is now interacting with the environment in a structured way, continuously ingesting air from one region, lifting it, rotating it, and exhausting it into stronger winds above. One reason wind shear matters so much in outbreaks like this one is that it allows storms to survive longer than ordinary air mass thunderstorms. A weakly sheared atmosphere may still produce brief storms on a hot and humid day, but those storms often rain into themselves and collapse. In a sheared environment, the storm leans. Its updraft tilts, its precipitation falls somewhat away from the inflow, and the whole system can persist much longer. Persistence gives the storm more time to intensify, more time to grow hail, more time to interact with boundaries, and more time to develop low-level rotation. This is why the same amount of instability can produce very different results depending on the wind profile. Strong instability without strong shear may lead to vigorous but disorganized storms. Moderate to strong instability with strong shear can lead to fewer storms, but much more dangerous ones. Meteorologists often use quantities such as storm relative helicity to estimate how much streamwise rotation is available to a storm. In simple language, this measures how favorably the wind profile aligns with the motion of a thunderstorm, allowing the storm to ingest air that already carries rotational character. When those values are high, the lower atmosphere is especially supportive of rotating updrafts. The air does not merely rise into the storm, it rises while already curved and turning relative to the storm's path. This makes it easier for rotation to concentrate in the updraft. In the context of a major outbreak, high storm relative helicity is one of the signs that forecasters watch with particular care, especially near fronts and warm frontal zones where surface winds may be backed, meaning they blow from a more easterly direction than usual. That backing increases the turning of wind with height and enhances the rotational environment. Wind shear also varies across the storm system. Some areas may have strong deep layer shear but weaker low-level turning. Other areas, especially closer to a warm front or low-pressure center, may have lower cloud bases and stronger low-level directional change. Those local differences help explain why certain corridors become more favorable for tornadoes, even when the broader threat region is much larger. The wind profile is not just a background statistic. It is the internal scaffolding of the outbreak, shaping how storms lean, rotate, and maintain themselves. Without wind shear, instability might still produce thunder, heavy rain, or brief downbursts. With wind shear, the atmosphere acquires memory and direction. It allows storms to become coherent systems rather than temporary bursts. It allows rising motion to be coupled with organized rotation. It allows the broad pattern of the outbreak to translate into individual storm structures capable of producing the most dangerous forms of severe weather. The air above the warm sector is therefore not merely fast. It is layered in a way that stores turning motion and offers it to any storm strong enough to use it. Once that storm begins to rise through the sheared environment, the invisible architecture of the wind becomes visible in the behavior of the storm itself, and the atmosphere moves one step closer to the rotating violence that can later reach the ground. Even in an atmosphere rich with moisture, strong with instability, and structured by wind shear storms, do not rise freely everywhere at once. Something still has to begin the upward motion in a focused way. That final requirement is the trigger mechanism. A trigger is the process that forces air upward strongly enough to overcome any remaining resistance and begin deep storm growth. Without a trigger, the warm sector can remain tense but quiet for hours. The air feels heavy, clouds may pass overhead, and meteorologists may watch a favorable environment hold together without immediate release. Then a boundary sharpens. The cap weakens, low-level convergence increases, and the first towers begin to rise. The atmosphere changes from stored potential to active convection. The trigger is therefore the moment of release, the point where readiness becomes motion. Several kinds of triggers can operate during an outbreak, and in the most dangerous patterns, more than one is present at the same time. The cold front is one of the most obvious. As denser air advances, it lifts the warmer air in its path. This lift can be broad and strong, especially when the front is well defined and the temperature contrast behind it is large. Along the front, warm air that had been resting in relative balance is forced upward whether it is ready or not. If the air is already moist and unstable, thunderstorms can form quickly along this zone. The dry line can do something similar, though, through moisture contrast, rather than pure temperature contrast. Warm dry air and warm moist air meet, and the difference in density and mixing characteristics sharpens the boundary. During the day, dry air often mixes downward more efficiently, helping the dry side deepen and push eastward. Where it meets the moist air parcels can be forced upward into the growing instability above. The warm front is another trigger, though its influence is often more subtle. Because it represents warm air gliding over cooler surface airlift, along it may be gentler and more widespread. Yet the wind and moisture contrasts near that boundary can be especially favorable for rotating storms once they do form. The surface, low itself, also acts as a trigger, not as a narrow line, but as a region of convergence where air flows inward from different directions. Convergence means that air is gathering horizontally, and when air gathers near the ground, it often has no place to go but up. The closer the flow becomes to the low and its associated boundaries, the more likely that scattered pockets of rising motion will deepen into storms. Smaller scale triggers can also matter. Outflow boundaries left behind by earlier storms, subtle zones where cooled storm air meets the undisturbed warm sector may become new lifting surfaces later in the day. Terrain can contribute modestly in some regions, and differential heating between cloud-covered and sunny areas can create local circulations that strengthen lift. In a volatile environment, these smaller triggers may be enough to decide where the first isolated storm forms, and the first storm can matter greatly, because early development may determine whether the day favors discrete supercells or a quicker evolution into a line. The cap plays an important role in the timing of triggers. This warm layer aloft suppresses rising parcels until lift becomes strong enough, or the cap weakens enough to let them pass through. In a weakly capped environment, storms may form too early and too broadly, spreading out energy and leading to messy clustered convection. In a strongly capped environment, storms may fail to form at all despite impressive ingredients on paper. The most dangerous situations often occur when the cap holds through much of the day, allowing instability to increase, and then erodes near a front dry line or other convergence zone during the late afternoon or evening. The release is then concentrated in space and time. Fewer storms form at first, but those storms form in an environment that is maximally prepared to support severe development. This is why forecasters care so much about not just whether storms will form, but when and where the trigger will succeed. The trigger also helps determine storm mode. If lift is concentrated along a narrow, fast-moving front, storms may quickly merge into a line. If lift is more isolated along a dry line, bulge, or discrete convergence zone, storms may remain separate for longer, increasing the chance of mature supercells. If lift spreads gradually along a warm frontal zone, storms may be fewer in number but highly efficient at tapping low-level rotational energy. The trigger is therefore not only the start of storms, it is also part of the reason those storms take one shape rather than another. In an outbreak like this, 1-2 rounds of triggering may occur in sequence. Afternoon storms can form first along the dry line or ahead of the main front where surface heating has been strongest. Later, as the cold front advances and large-scale lift increases, a second round may organize into a broader line of storms that continues after dark. The atmosphere does not simply fire once. It can release its energy in stages each trigger, drawing on a slightly different part of the environment. This staged release is one reason outbreaks become so prolonged and exhausting. A region may experience initial isolated storms, a temporary lull, and then a nocturnal line with renewed tornado and wind potential. The trigger mechanism ties all previous ingredients together. Moisture provides fuel. Instability provides upward potential. Wind shear provides structure and rotation. The trigger is what forces the first serious motion through the cap and into the open atmosphere. It is the hand that opens the gate. Once that gate opens, the warm sector is no longer just loaded. It begins to spend what it has stored. Clouds rise faster, towers harden into storms, and the invisible imbalances of the day start taking visible form. From the outside, this can look sudden, as though the sky changed its mind in a matter of minutes. In reality, the sky has been preparing for hours. The trigger simply marks the moment when preparation ends and the atmosphere commits itself to action. When the atmosphere finally releases its stored energy in a strongly sheared environment, one possible result is the discrete supercell. This is the storm form that severe weather forecasters often watch most closely because it combines longevity, internal organization, and the ability to concentrate multiple hazards within a single cell. A discrete supercell is not simply a large thunderstorm. It is a storm that remains relatively isolated from neighboring storms while sustaining a deep rotating updraft. Isolation matters because a storm that stands apart from others can draw in warm, moist air from the surrounding environment without as much interference. Rotation matters because it helps the storm maintain structure, separate inflow from precipitation, and persist far longer than an ordinary pulse storm. In an outbreak like this one, the window during which storms remain discrete can be one of the most dangerous phases of the entire event. The life of a supercell begins with a rising tower, but the important difference appears as the updraft matures within strong wind shear. Air enters the storm from the lower atmosphere, carrying warmth, moisture, and a favorable turning profile. As the updraft strengthens, it tilts horizontal spin into the vertical and begins to rotate through depth. Once that rotation becomes persistent and organized, the storm is no longer behaving like a random convective burst. It has developed a mesocyclone, a rotating region within the updraft that can extend through a large part of the storm. This rotating core influences almost every other process inside the thunderstorm. Rain and hail are redistributed. Downdrafts form in characteristic locations. The storm's visual structure often becomes more distinct, with a rain-free base in one area, heavier precipitation wrapping around another, and a clear sense that the storm is being shaped from within, rather than simply blowing apart in the prevailing wind. The reason discrete supercells are so efficient is that rotation and shear work together to protect the storm's inflow. In an ordinary thunderstorm, falling rain and descending cooled air can choke off the warm air supply that originally fed the updraft. The storm collapses into its own outflow. In a supercell, the tilted and rotating updraft keeps much of the precipitation displaced from the main stream of warm inflow. This allows the storm to keep ingesting energy while also producing large amounts of rainhail and potentially damaging downdrafts. The storm becomes self-sustaining for longer periods. It does not last forever, but it often survives long enough to travel many miles, interact with boundaries, and undergo internal changes that can increase tornado potential. The environment around a discrete supercell also remains important. A storm moving through open, warm sector air can continue feeding on high instability and strong low-level moisture. If it crosses a subtle boundary, such as an old outflow edge or the warm frontal zone, the local wind field may become even more favorable for low-level rotation. This is why forecasters track not only the storm itself, but also the exact environment into which it is moving. Two supercells on the same radar screen may behave differently because one encounters richer inflow or stronger near-surface turning than the other. A discrete supercell is therefore both an individual storm and a mobile interaction with the larger environment. Each mile matters. Each shift in low-level wind or moisture can matter. Each minute of isolation from neighboring storms can matter. Visually and dynamically, supercells often develop recognizable features. A flanking line of smaller towers may feed into the main updraft. A broad anvil spreads downstream at upper levels as the storm exhausts into the stronger winds aloft. The precipitation core may wrap around one side of the storm, while the inflow side remains relatively clearer. Near the base, the lowering associated with the rotating updraft may become more distinct. These features are not decorative. They reveal the internal organization of the storm and the way air is circulating through it. The strongest supercells can produce giant hail because the rotating updraft keeps embryonic hailstones suspended long enough to grow through repeated cycles in the cold upper storm. They can produce intense straight-line winds because downdrafts transport momentum from aloft downward and spread it out along the surface. Most importantly, in the context of a tornado outbreak, they can concentrate low-level rotation beneath the mesocyclone, setting the stage for tornadogenesis, if the near-ground processes align. The discrete phase of an outbreak is often fragile. It may last only a few hours before storms begin interacting and merging. That briefness is part of why it is so dangerous. A relatively small number of isolated storms can do disproportionate damage during that period, because each storm is operating at high efficiency in an environment that has not yet been disrupted by widespread outflow. Once more, storms form nearby cold pools expand, and boundaries become tangled. The atmosphere grows messier. The cleanest supercell structures often exist before that transition. During those hours, a single cell may become the dominant threat over a large area. It can produce large hail-damaging winds and potentially a long-track tornado, all while moving steadily through populated corridors. In forecasting language, there is often concern about whether storms will remain discrete or quickly upscale into a line. That concern is not academic. It is a statement about how the atmosphere may choose between two severe modes. Discrete supercells favor concentrated, often intense localized threats, especially significant tornadoes and very large hail. A line favors broader wind damage and embedded tornadoes. Both are dangerous, but the isolated phase can be uniquely alarming because it gives a storm room to mature fully. In this outbreak, the discrete supercell represents the atmosphere in one of its most organized severe states, a stage in which all previous ingredients meet in a single storm that is separated from its neighbors, anchored in rich inflow, rotating through depth, and capable of turning a broad environmental threat into one focused moving engine of destruction. Inside a mature supercell, the possibility of a tornado depends on a final concentration of motion near the ground. The storm already rotates aloft through its mesocyclone, but a tornado requires more than broad rotation in the middle levels of the cloud. It requires the narrowing, strengthening, and downward extension of that rotation into the lowest part of the atmosphere, where it can connect with the surface and become a violent column of spinning air. This transformation is called tornadogenesis, the birth of a tornado. It is one of the most studied and most complex processes in severe weather, not because the broad ingredients are mysterious, but because the final step depends on a delicate interaction between inflow downdrafts, pressure changes, and stretching of rotating air in a very small region compared with the size of the storm. The supercell provides the larger rotating framework, but the tornado emerges only when the lower part of that framework becomes sharply concentrated. Rotation can intensify when a column of air is stretched vertically. This is the same physical principle seen in many spinning systems. When the column becomes taller and narrower, the spin can increase. In a storm, strong upward motion can stretch low-level rotation and make it tighter. But there must first be enough rotation present close to the ground. Some of that comes from the storm's ingestion of a favorable shear profile. Some may be enhanced near local boundaries, where surface winds shift and increase the turning of the lowest air. Within the storm, low-level inflow carries this air toward the mesocyclone. As it converges and rises, the rotation becomes more focused. At the same time, rain-cooled air descending through parts of the storm creates downdrafts. One of the most important of these is the rear flank downdraft, a region of descending air that wraps around the backside of the rotating updraft. This descending air is not simply an accessory to the process. It helps shape the pressure field and the wind field near the base of the storm. In many tornado-producing supercells, the rear flank downdraft wraps around the mesocyclone in such a way that warm inflow and cooler descending air are brought into close contact. The exact temperature and moisture character of that downdraft matters. If it is too cold and dense, it can undercut the updraft and weaken the near-ground circulation. If it is only modestly cooler and still able to wrap the rotation without choking the inflow, it can help tighten the circulation instead. This is one reason tornado formation remains difficult to predict at the smallest scale. The storm may look favorable on radar, yet the detailed thermodynamic balance near the base determines whether the circulation contracts into a tornado or remains broader and less efficient. Pressure also plays a central role. As rotation strengthens, pressure tends to fall in the center of the circulation. Lower pressure encourages air to flow inward. As that inward-moving air approaches the axis of rotation, its angular momentum is concentrated into a smaller radius, and the spin increases. The result can be a feedback process in which stronger rotation lowers pressure further, which draws in more air, which tightens the circulation more. Once this narrowing becomes sufficiently strong and vertically connected, a tornado can condense visibly as pressure drops and moisture in the air rapidly cools into cloud droplets. The visible funnel, however, is not the tornado itself in the strictest sense. The tornado is the rotating wind. Sometimes the visible condensation does not reach all the way to the ground at first, even while damaging winds are already occurring below. In other cases, debris lifted from the surface reveals the connection before the full funnel becomes obvious. This is why radar spotter reports and damage confirmation are all important in operational forecasting. Tornado formation is often described as a sequence, but in reality, it can be uneven and fast. The low-level mesocyclone strengthens. A wall cloud may develop beneath the rotating base as inflow rises and condenses. A narrow circulation forms. Debris begins to rise. The visible funnel may descend, widen rope out, or cycle. The tornado may remain on the ground for only a few minutes, or it may persist for a long track if the parent storm continues to support it. Some supercells produce multiple tornado cycles, with one tornado weakening as another circulation develops nearby, under the same larger rotating updraft. This cyclic behavior reflects the storm's ongoing internal evolution rather than a single one-time release. The tornado is therefore not always the end point of a storm. It can be one phase in a continuing rotating system. Near-surface conditions strongly influence whether tornadogenesis succeeds. Lower cloud bases, richer moisture, and stronger directional shear in the lowest kilometer tend to favor the process. These ingredients help the storm maintain a tighter connection between the rotating updraft and the air just above the ground. Boundaries, such as warm fronts or old outflow edges, can enhance these conditions locally, which is why tornadoes sometimes occur in a narrow corridor, even when many storms are present across a larger region. The environment does not need to be perfect everywhere. It needs to be favorable where the storm is at that moment. This makes tornado forecasting both scientifically grounded and operationally difficult. Meteorologists can identify broad zones where supercells are likely and where low-level rotation is more probable. Determining which specific storm will produce a tornado and when still depends on smaller processes unfolding inside the storm in real time. In the context of this outbreak, understanding tornado formation means seeing it not as a random act, but as the result of repeated atmospheric steps. Moist air rises into instability. Shear creates the possibility of organized rotation. A supercell forms and sustains a mesocyclone. Low-level inflow downdrafts pressure falls, and vertical stretching then work together in a small region beneath the storm. When those processes align, the storm's broad rotation condenses into something narrower, stronger, and far more destructive. The tornado appears to descend from the cloud, but physically, it is the storm drawing together motion that has been present in pieces all along, tightening it until the air itself becomes a rotating column capable of tearing across the surface below. When tornadoes occur after dark, the underlying physics remain the same, but the human and observational environment around them changes profoundly. A nocturnal tornado is not born from a different atmosphere than a daytime tornado. It still depends on instability, wind shear lift, and the organization of a parent storm. What changes at night is the way those ingredients are maintained, the way storms are perceived, and the way people respond to warnings. Darkness removes one of the most important forms of confirmation available during the day: simple visual awareness. During daylight, a storm can be seen building on the horizon. The sky may darken in a recognizable way. Lowerings beneath the storm may become visible. People may notice hail, a wall cloud, or rapidly changing structure before the tornado itself forms. At night, most of those cues disappear. The sky becomes a black background against which only lightning briefly reveals the storm's shape. The tornado may be fully wrapped in rain, hidden inside the broader circulation, and invisible until it is already very close. This is one reason nighttime tornadoes are often more deadly relative to their intensity. The danger is not only meteorological, it is also perceptual and behavioral. Night changes the boundary layer, the lowest part of the atmosphere that interacts directly with the ground. After sunset, the surface often cools, which can reduce instability near the immediate ground in some situations. On a quiet night, that cooling may suppress storm development. In a major outbreak, however, the larger system often compensates for the loss of solar heating. The low-level jet can strengthen after dark, increasing the transport of warm, moist air above the surface and enhancing wind shear in the lowest few thousand feet. This nocturnal strengthening is one of the most important reasons severe storms can remain dangerous long after sunset. The surface may cool slightly, but the atmosphere a short distance above it can become even more favorable for organized convection. Storms already in progress may continue feeding on that inflow, and new storms may develop or intensify along advancing boundaries. The result is an environment in which tornado potential can remain high or even increase overnight, despite the absence of daytime heating. This can seem counterintuitive from a human perspective, because nighttime often feels calmer. In reality, the atmosphere may be reorganizing into an especially efficient severe weather state. Night also changes storm mode in many outbreaks. Discrete supercells that formed in the afternoon may merge into a line as cold pools spread, and the forcing along the main front strengthens. That line, often a quasi-linear convective system, can still produce tornadoes, but they are typically smaller, faster evolving, and embedded within heavy precipitation. Even when supercells remain somewhat isolated, after dark rain wrapping around the circulation often hides the tornado from view. A daytime tornado crossing open land may be visually dramatic from a distance. A nighttime tornado inside rain appears instead as wind sound, power flashes, and sudden damage. People do not see the threat approaching in the same way. They hear it, if they hear it at all, only when it is already very near. Operationally, nighttime reduces the value of direct visual spotter reports. During the day, trained observers and the public may confirm funnels, wall clouds, debris, or ground circulation. At night, radar becomes even more central. Meteorologists rely more heavily on velocity signatures, debris signatures, and storm relative motion to infer what is occurring near the ground. Modern radar is powerful, but it still samples the atmosphere above the surface at increasing heights, with increasing distance from the radar site. That means the lowest and most critical part of the circulation is not always observed directly. Warnings can still be issued effectively, but the uncertainty around exact surface behavior may be larger, especially in fast-moving lines. This makes the timing of warnings even more important and the response to warnings even more critical. Nighttime also changes vulnerability. People are more likely to be asleep, less likely to receive outdoor cues, and slower to act if awakened abruptly. Mobile homes and other vulnerable structures remain especially dangerous places during nocturnal tornado events, because there may be less time to relocate safely once a warning is received. Power failures add another layer of risk by disrupting lighting, charging access, and sometimes communications. Roads are harder to navigate in darkness and heavy rain. Debris is harder to see. Flash flooding combined with severe weather becomes more dangerous because inundated roadways are less visible and escape routes are harder to judge. The same storm system that produces a hidden tornado may also be dropping intense rain nearby, multiplying confusion during the hours when decision-making is already impaired by fatigue and darkness. The social rhythm of the night matters as much as the meteorological rhythm. Families are indoors, schools and workplaces are inactive, but hospitals, emergency services, and utility crews must function in more difficult conditions. A warning issued in the afternoon reaches people during active hours when phones are in hand and attention is higher. The same warning issued after midnight reaches people in fragments through alarms, broadcast interruptions, and automated alerts that must cut through sleep. This is why preparedness language around nighttime severe weather often emphasizes redundant warning systems. The storm cannot be made less dangerous, but the chance of waking in time can be improved. From the atmospheric perspective, the night is not a pause in the outbreak. It is simply another phase 1, in which inflow may strengthen storms, may organize differently, and low-level rotation may remain potent while visibility collapses. From the human perspective, it is often the most dangerous phase because the storm becomes harder to confirm, harder to track with the senses, and harder to flee. The tornado itself is still a rotating column of air born from the same processes described earlier. What darkness adds is concealment. It hides the structure, shortens the practical reaction window, and turns an already violent storm into something more sudden and more difficult to survive. Not because the atmosphere is acting by different rules, but because the same rules are now unfolding in a world that cannot see them. As the outbreak matures, isolated supercells do not always remain isolated. Their cold outflows spread, their precipitation fields expand, and the larger forcing along the front begins to dominate the smaller separations that had earlier allowed individual storms to stand apart. When this happens, the atmosphere shifts from one severe mode into another. Separate storms begin to link into a longer band, and the event evolves into a squall line, or in more technical language, a quasi-linear convective system. This transition is important because it does not end the tornado threat. It changes its structure. The storm is no longer organized around one dominant rotating updraft moving through open warm sector air. Instead, the severe weather becomes embedded within a continuous or nearly continuous line of storms, often extending for many miles. The line is efficient at producing widespread damaging winds, but within it, smaller zones of rotation can still intensify and generate tornadoes. These rotating pockets are called mesovortices. And they are one of the reasons linearly organized storms remain dangerous long after the discrete supercell phase has ended. A squall line forms when multiple convective cells develop along or near the same forcing boundary, usually a cold front or a strong prefrontal convergence zone, and then merge as their outflows expand. The merged system develops a leading edge where cold storm outflow meets the warm air ahead of it. That edge is called the gust front. Physically, it is the advancing boundary of denser rain-cooled air spreading outward near the surface. As this denser air pushes forward, it lifts the warm, moist air ahead of it, sustaining new storm growth along the line. The line therefore maintains itself by continuously forcing fresh inflow upward at its front edge. It becomes a moving atmospheric machine, fed by the same moisture and instability that earlier supported supercells, but now shaped by collective organization rather than individual storm isolation. The most obvious hazard in a squall line is often straight-line wind. Descending air from many cells combines with the forward surge of the cold pool, and momentum from stronger winds aloft can be transported downward. The result can be widespread swaths of damaging wind extending across several states. Trees fall, power lines fail, roofs are damaged, and infrastructure is stressed over a broad corridor rather than in a narrow tornadic path. Yet embedded within this broader wind field, the line may contain local bows, kinks, surges, and areas of enhanced shear. Those localized distortions matter because the gust front is not a uniform wall. It is a moving boundary with sharp contrasts in temperature, density, and wind. Along that boundary, horizontal spin can develop or intensify. When that spin is stretched and tilted within a small portion of the line, a mesovortex can form. A mesovortex is a compact area of rotation embedded within the larger line of storms. It is not as broad or persistent as the mesocyclone of a mature supercell, but it can still be intense enough to produce tornado-force winds and, in some cases, a true tornado at the surface. The mechanism differs somewhat from the classic supercell pathway. In a line, the rotation often develops directly along the leading edge where the cold outflow collides with warm inflow. Wind on one side of the boundary differs sharply from wind on the other. Small perturbations can be amplified by the shear concentrated there. Once a circulation develops upward motion along the gust front, can stretch it and intensify it quickly. Because these processes occur within a line already full of rain and embedded convection, the resulting tornadoes are often fast-forming, short-lived, and difficult to detect visually. They may be wrapped completely in precipitation and hidden at night, making radar and warning systems especially important. One of the reasons quasi-linear convective systems are so challenging operationally is that they can produce both broad and local damage simultaneously. A community may experience widespread severe wind over many miles of line, while a narrower zone within that line experiences concentrated rotation and a more tornadic damage pattern. To a person on the ground, the distinction may be unclear in real time. The storm arrives as a roaring wall of rain and wind with embedded circulations that may only reveal themselves through sudden intensification, structural failure, or radar detection from meteorologists monitoring the line. The transition from supercells to a line is not always complete or immediate. Some parts of the system may retain semi-discrete characteristics, while others merge. Embedded supercell structures can persist for a time within a broader convective band, especially if the environment still supports strong deep-layer shear. This makes the line a mixed system with multiple storm-scale processes operating at once. A bowing segment may indicate stronger forward momentum and enhanced damaging wind. A notch or break in reflectivity may mark localized inflow. A small rotational signature along the leading edge may signal mesovortex development. The line is therefore not simpler than the supercell phase. In some ways, it is more complex, because severe processes are distributed along a moving boundary rather than concentrated in one isolated storm. In an outbreak like this one, the nocturnal phase often favors this mode. As evening progresses, large-scale forcing strengthens. Along the front, outflows merge, and the system organizes into a long-lived band that pushes eastward through populated regions. The danger broadens geographically, even if the individual tornadoes become smaller or shorter-lived on average than those of the discrete phase. The line covers more ground, affects more people, and continues through the hours when visibility and response are weakest. The atmosphere has not calmed, it has reorganized. The same ingredients of moisture, lift, and shear are still present, but now they are expressed through a linear storm system whose leading edge acts as both engine and hazard zone. Mesovortices are the hidden sharp points inside that broader force, proving that when storms merge, rotation does not disappear. It adapts to the new structure, remaining capable of producing sudden, dangerous tornadoes, even as the outbreak shifts from isolated storm towers to one long moving front of wind rain and embedded spin. Inside severe thunderstorms, not every destructive force takes the form of a tornado. Two of the most widespread and damaging hazards, hail and straight-line wind, arise from the internal circulation of the storm itself and often affect far larger areas than any single tornadic path. In a major outbreak, these hazards are not secondary details. They are parallel expressions of the same energetic atmosphere. A storm with a powerful updraft and strong environmental shear can grow hail to exceptional size, while also generating downdrafts capable of producing devastating wind damage at the surface. These outcomes depend on how air, water, and ice move through the storm column, and they reveal how the internal structure of a thunderstorm can turn invisible atmospheric energy into physical impacts on the ground. Hail begins high within the storm in the region where temperatures are well below freezing. Strong updrafts carry water droplets upward into cold air, where they become supercooled, meaning they remain liquid, even though their temperature is below the freezing point. When these droplets collide with small ice particles, they freeze on contact and begin building hailstones layer by layer. The process is not a single upward trip. In a strong storm, a growing hailstone may be lifted, fall lifted again, and pass through different regions of water and ice many times. Each circuit adds new layers. The stronger the updraft, the larger the stone can become before gravity finally overcomes the rising air and allows it to fall to the ground. This is why large hail is a sign of storm strength. A thunderstorm cannot produce very large hail unless it has a deep and intense updraft capable of suspending heavy ice for long periods. The rotation of a supercell can make this process even more efficient by organizing the internal flow and helping separate the hail growth region from the heaviest precipitation core. Hail damage depends not only on size, but also on fall speed. Larger stones fall faster and strike with greater force. Small hail may shred leaves or make noise on rooftops. Large hail can shatter glass, destroy vehicles, damage roofs, injure livestock, and cause serious injury to people caught outside. In agricultural regions, a single hail core can strip fields in minutes. In urban areas, it can produce widespread insurance losses across thousands of homes and vehicles. The danger is not theatrical. It is mechanical. Ice falling at high speed transfers momentum on impact, and the larger the stone, the more violent the result. During outbreaks with strong instability and supercells, hail can reach extraordinary size because the storm's upward motion is powerful enough to support repeated growth cycles. Hail is therefore one direct measure of how energetic the storm has become in the vertical dimension. Straight-line wind forms through a different pathway, though it is also tied to the storm's internal balance between rising and sinking air. As precipitation grows and begins to fall, some of it evaporates into drier air below cloud base. Evaporation cools the surrounding air, making it denser. Meltwater and drag from falling rain and hail can also pull air downward. The result is a downdraft, a descending current of cooler, denser air within the storm. When that downdraft reaches the ground, it spreads outward, sometimes violently. If the descending air also brings down momentum from faster winds higher aloft, the resulting surface winds can become extremely strong. These winds are called straight-line winds because their damage pattern usually spreads outward or along one general direction, unlike the convergent and rotational pattern more typical of a tornado. Yet the distinction is not always obvious in real time to those experiencing the storm. Straight-line wind can sound like a train rip off roofs, topple trees and snap power poles with a force that feels tornadic, even when no tornado is present. In squall lines and bow echoes, this wind hazard becomes especially important. A bow echo is a segment of a storm line that surges forward, creating a bowed shape on radar. This shape often indicates stronger winds pushing the line outward. The bow develops because descending air and the cold pool behind the line accelerate forward, enhancing the damaging wind threat along and just behind the leading edge. In widespread outbreak conditions, these features can produce corridors of destruction extending for dozens or even hundreds of miles. Power outages become widespread. Roads are blocked by fallen trees. Emergency response is strained over a broad area instead of concentrated along one narrow path. This is one reason severe wind events can be as disruptive to infrastructure as more visually dramatic tornadoes. They strike more territory and affect more people at once. Hail and straight-line wind also interact. A storm strong enough to support giant hail often has intense internal gradients of temperature and momentum, which means powerful downdrafts may not be far behind. In some cases, a supercell begins with a major hail threat during its mature rotating phase and later transitions towards stronger downburst or rear flank wind damage as its internal balance shifts. In other cases, a line of storms produces mainly wind, while smaller embedded circulations or stronger cells within the line produce pockets of severe hail. The internal distribution of these hazards depends on storm structure, moisture profile, and the depth of dry air available for evaporation. That means the same outbreak can produce shattered windshields in one county and widespread tree loss in the next, even though both are being driven by the same broader system. Unlike tornadoes, hail and straight-line winds often affect many places simultaneously. Their warning challenge is therefore broader. A tornado may threaten a narrower corridor. A hail core and a severe wind swath may cover an entire metropolitan area. These hazards also remain dangerous when visibility is poor because a person may not understand the severity until the impact begins. Hail can strike suddenly with explosive force. Straight-line wind can intensify within seconds as a downdraft reaches the ground. During the nighttime phase of an outbreak, these dangers become even harder to assess from ordinary observation. Their scientific cause, however, remains rooted in the same principles already present throughout the storm. Strong updrafts build hail aloft. Cooling and loading create downdrafts. Shear organizes the storm so these processes can intensify, rather than cancel one another out. In that sense, hail and straight-line wind are not side effects of severe storms. They are central products of the storm's internal circulation, different from tornadoes in form, but equal in their capacity to damage homes, landscapes, crops, cities, and power systems across a vast swath of the outbreak. Beyond the warm sector where tornadoes, hail, and severe wind dominate attention, the same storm system produces very different hazards in colder and wetter parts of its circulation. This is one of the defining features of a large spring outbreak. The atmosphere is not dangerous in only one way. It expresses its energy according to the thermal structure of each region. In one sector, deep moisture and instability lead to towering convection and violent rotation. In another, prolonged descent over cooler air produces flooding rain. Farther north, where surface temperatures remain near or below freezing, that same moisture falls through layers of cold air and becomes freezing rain, sleet, or heavy snow. The result is not a collection of unrelated weather events, but a single organized system with multiple hazard zones, each shaped by the local temperature profile and motion of the air. Flooding develops most readily where the atmosphere can lift large amounts of moisture repeatedly over the same area or release rain faster than the ground, and drainage systems can absorb it. In the warm and moist part of the storm, air rising along fronts or within repeated bands of thunderstorms condenses great quantities of water. If storm cells move quickly and do not repeat, the rain may still be intense but more temporary. If new storms keep forming over the same corridor and tracking along the same path, a process often called training, rainfall totals can rise rapidly. Urban areas are especially vulnerable because pavement limits absorption and channels water into streets, underpasses, and drainage networks that can be overwhelmed in a short time. Rural terrain has its own vulnerabilities. Creeks rise quickly, low water crossings become traps, and saturated soils lose their ability to absorb additional rain. Flash flooding is therefore not only a matter of total rainfall, but also of rainfall rate, storm repetition, ground conditions, and local geography. In a large outbreak, the same atmospheric transport that supports severe storms farther west or south may continue feeding deep moisture into a rain shield farther east or northeast, where the storm mode is less about rotation and more about sustained water loading. On the colder side of the system, precipitation changes form because the vertical temperature structure changes. If snow forms aloft and falls through a layer of above freezing air, it may melt into rain. If that rain then falls into a shallow layer of sub-freezing air near the ground, it can become freezing rain. The drops remain liquid until they strike a surface at or below freezing, where they freeze on contact. This produces glaze ice on roads, tree branches, vehicles, and power lines. Freezing rain is one of the most infrastructure-intensive hazards in weather because even a modest coating adds large amounts of weight. Branches bend and snap. Utility lines sag under accumulated ice. Travel becomes hazardous because tires lose traction on what may look like merely wet pavement. The danger grows quickly because the freezing happens everywhere, exposed not only in one narrow path. A broad swath of the landscape becomes loaded with weight and slickness at once. If the cold layer is deeper, precipitation may refreeze before reaching the ground and fall as sleet, small ice pellets that can accumulate and reduce traction. If the air remains below freezing through most of the column, the precipitation falls as snow. In strong cyclonic systems, the northern and northwestern sectors often support heavy snow because moisture is abundant and lift remains strong while temperatures are cold enough for snow growth. If winds are also strong, the snowfall becomes more than an accumulation problem. It becomes a visibility problem and a transport problem. Fine snow is lifted and driven horizontally, reducing visibility to near zero. Roads close traffic stops, and the danger shifts from violent impact to isolation and exposure. Blizzard conditions do not require record snowfall by themselves. They require snow or blowing snow combined with sufficiently strong wind and low visibility for a sustained period. In a major spring system, that combination can occur at the same time tornadoes are forming several hundred miles away. The same low-pressure center helps produce both because it creates the broad circulation that pulls warm, moist air north on one side and wraps colder air around the other. The sharp temperature gradient across the system explains why these hazards can exist so close together. A single state may experience severe thunderstorms in its southern counties and icing or snow farther north within the same day. The boundary between these outcomes is not random. It reflects the depth of cold air near the surface, the track of the low, and the precise arrangement of fronts. Small shifts in storm track can move the ice zone north or south, alter where the heaviest snowband sets up, or determine whether a location receives cold rain instead of freezing rain. This sensitivity is one reason such events are difficult to manage. A slight forecast error in temperature profile can change the hazard type completely, yet the larger structure remains coherent. Moisture is being lifted. The atmosphere is cooling with height. The surface pattern determines what form that moisture finally takes. Floods, ice storms, and blizzards therefore belong to the same physical story as the tornado outbreak, even though they feel very different on the ground. Flooding represents too much liquid water delivered too quickly. Ice storm conditions represent liquid water freezing on contact in a shallow, cold layer. Blizzard conditions represent frozen precipitation combined with strong wind and reduced visibility. Each hazard depends on a different version of the same ingredients: lift moisture and a supportive temperature structure. In a continental outbreak, the remarkable feature is not merely that each happens. It is that they happen together under one circulation. The warm sector draws attention because tornadoes are sudden and visually dramatic. The colder and wetter sectors reveal something equally important about the system's scale. It is large enough and thermally complex enough to contain several seasons inside itself at once. The atmosphere is sorting its moisture into rain, freezing rain, or snow, according to the local structure of the air, and the land beneath responds with flooded streets, glazed power lines, or whiteout roads. All of these are chapters of the same storm, written in different forms across different parts of the continent. A severe weather outbreak becomes a human disaster only when atmospheric danger meets daily life, and that meeting is shaped by exposure infrastructure timing and the practical limits of warning systems. The atmosphere may be capable of producing tornadoes, flooding, ice accretion, blizzard conditions, and widespread wind damage, but the consequences depend on who and what lie in the path. Population density matters immediately. A strong storm crossing open farmland can still be destructive, but the same storm crossing a dense urban corridor encounters more homes, more roads, more power lines, more hospitals, more schools, and more opportunities for disruption. The damage is not only measured by wind speed or rainfall depth. It is measured by how many systems of ordinary life are forced into failure at once. A metropolitan area under severe threat contains vertical structures, aging trees, glass traffic networks, and electrical grids that behave differently from rural landscapes. More people may be sheltered in sturdy buildings, but more people may also be trapped by congestion, dependent on elevators, reliant on electrically powered medical equipment, or unable to respond quickly because they do not have access to a basement or reinforced shelter. Vulnerability is therefore not a simple urban versus rural contrast. It is a layered interaction between hazard type and human setting. Nighttime adds another layer of exposure because it changes awareness and decision-making. A warning delivered at midday reaches people who are awake moving and often already paying some attention to the weather around them. A warning delivered after midnight must overcome sleep, darkness, fatigue, and the possibility that a device is silenced, uncharged, or ignored. The storm itself may also be harder to verify because it is hidden in rain or darkness. This means the actual lead time between receiving a warning and taking meaningful shelter can be much shorter at night, even when the official warning time appears similar. People may spend the first crucial minutes deciding whether the alert is real, locating information, waking children, moving pets, or trying to find shoes keys and flashlights. In mobile homes or temporary housing, the danger is more severe because shelter quality may be inadequate from the start. Reaching a sturdier location requires travel precisely when roads may be wet, dark, blocked, or already under threat. The human timetable is slower than the storm timetable, and at night that mismatch grows worse. Forecasting itself has real limits. Meteorology can identify large areas of heightened risk, diagnose instability, and shear and detect radar signatures associated with rotation hail and damaging wind. Modern forecasting is vastly better than it was decades ago. Yet, it cannot remove uncertainty at the smallest and most important scales. A forecast may correctly identify the county corridor where tornadoes are more likely without being able to specify which exact storm will produce one an hour later. A line of storms may show embedded rotation on radar, but whether that circulation has tightened to the surface may remain uncertain until debris signatures or damage reports appear. Flood warnings may be based on rainfall estimates and hydrologic models, yet the exact road that washes out first depends on terrain drainage, maintenance, and small local channels that maps do not always resolve fully. The atmosphere is continuous and fluid. Warning systems divide it into polygons, time windows, and alert categories because people need operational decisions. That translation is necessary, but it introduces practical limits. Warnings must sometimes be issued before certainty is complete, because waiting for certainty would cost lives. This creates a difficult balance between precision and caution. Too little warning is dangerous. Too many warnings that produce no local impact can reduce urgency over time. Infrastructure determines how quickly atmospheric stress becomes social failure. Power systems are a clear example. Straight-line winds, ice loading, or falling trees can interrupt electricity across large regions. Once power fails, refrigeration, medical devices, traffic signals, water pumping, internet access, and communication charging all become more fragile. Hospitals and emergency centers often have backup systems, but those systems are designed for contingencies, not unlimited strain. Flooding can isolate neighborhoods and slow emergency response. Snow and ice can close roads and delay repair crews. A tornado path, even if narrow, can sever local communication and transport at exactly the moment when information matters most. The system's multi-hazard nature compounds these problems. A region may not be dealing with one cleanly defined emergency, but with overlapping ones: severe wind plus flooding ice, plus power loss, tornado warnings, plus road closures. Response becomes more complex because the correct safety action changes by hazard. Basement shelter may be right for a tornado, but not useful if the threat is rising floodwater. Travel may be dangerous under ice or blizzard conditions, even if a formal tornado threat is low. Public understanding must therefore keep pace with changing threats, and that is difficult when the same storm system presents different instructions across short distances and changing hours. Social factors also matter. Some households do not receive alerts in their preferred language. Some lack reliable internet or weather radio access. Some people have prior experience that makes them underestimate danger, while others have limited shelter options regardless of what the forecast says. Schools, nursing homes, prisons and hospitals all face distinct constraints in moving or protecting large groups of people. Risk is therefore not evenly distributed, even inside the same warning polygon. Meteorology can describe the atmosphere, but impact depends on how that atmosphere meets the unequal geography of human life. In an outbreak like this one, the atmosphere tests not only buildings and trees, but also systems of communication, trust and timing. Forecast officers, broadcasters, emergency managers, utility crews and households all become part of the event. The storm is no longer only a physical process in the sky. It becomes a chain of decisions made under uncertainty and under pressure. That chain is where danger turns into loss, or sometimes where preparation successfully interrupts that path. The human story of the outbreak is therefore not separate from the meteorological story. It is the final medium through which the storm expresses itself, revealing that the true severity of a weather event lies not only in wind or rain, but in the points where atmospheric force meets the structures and routines on which ordinary life depends. When the outward mechanics of the outbreak have been fully traced from the continental arrangement to the jet stream, the fronts, the moisture return, the instability, the shear, the triggers, the supercells, the tornadoes, and the wider zones of flood ice and snow. The deepest layer of meaning lies in a broader question of repetition. Events like this are often remembered first as singular days, a night of tornadoes, an ice storm in early spring, a corridor of flash flooding a line of destructive wind. Yet over time, what begins to draw attention is not only the force of one event, but the sense that compound event storms, carrying several seasonal identities, at once appear with increasing frequency in public experience. This perception matters, but perception alone is not enough. The scientific question is not whether a particular outbreak feels unusual. The question is what observations show over time, what physical principles support those observations, and where uncertainty remains. Climate research does not claim that every tornado outbreak or every spring storm is directly caused by global warming in a simple one-to-one way. Severe convective weather is influenced by many interacting factors across multiple scales, from continental moisture transport and synoptic forcing to storm-scale boundaries and minute changes in low-level wind. Tornado occurrence itself is especially difficult to interpret in long records because observation methods have changed, radar coverage has improved, population has shifted, and weaker tornadoes are detected more consistently now than in earlier decades. This makes simple counts a poor guide to deeper understanding. Even so, some broader patterns are clearer than others. A warmer atmosphere can hold more water vapor. This is one of the most robust physical relationships in climate science. When temperatures rise, the air's capacity for moisture increases, and in environments where moisture is available that can support heavier rainfall. This does not mean every storm produces extreme rain, but it does mean the atmosphere is more capable of doing so. In systems like this one, where deep moisture is already being drawn northward and lifted over large regions that added capacity matters. It can increase the ceiling for heavy precipitation and heighten the risk that rainfall becomes overwhelming when storms train over the same ground. This is one area where scientific confidence is relatively strong. Heavy precipitation events have increased in many regions, and the thermodynamic explanation is well established. The relationship between warming and tornado environments is more complex. Tornadoes depend not only on moisture and instability, but also on wind shear storm initiation and mesoscale structure. Climate change may influence some of these ingredients in different directions. Warmer lower levels can increase instability in many situations, especially where moisture is abundant. At the same time, the large-scale wind patterns that create shear may not increase in a simple parallel way and can vary by season and region. The result is not a single obvious trend that applies everywhere. Instead, researchers often examine environments favorable for severe thunderstorms rather than tornado counts alone. Some studies indicate that favorable environments may become more common in certain seasons or shift geographically, especially into cooler parts of the year and farther east in some analyses. There is also growing discussion of clustering the idea that severe storm days may become less evenly distributed with longer quiet periods interrupted by more concentrated bursts of activity. Observations support concern about such changes, but the precise causes and future trajectory remain active areas of research. What can be said with greater confidence is that compound events deserve special attention. A compound event is not merely a strong hazard. It is a system in which several hazards occur together or in close sequence, amplifying impacts, because infrastructure and emergency response are strained in multiple ways at once. A storm that produces tornadoes, flooding, and power-disrupting wind already creates more risk than any of those hazards alone. Add ice, snow, or heat on different sides of the same circulation, and the event becomes harder to prepare for and harder to recover from. Climate research increasingly recognizes that societal risk often grows through these overlaps, rather than through one variable in isolation. A warmer climate does not need to create a brand new kind of storm to increase danger. It can increase stress by making some parts of familiar systems wetter longer, lasting more spatially extensive, or more likely to interact with vulnerable infrastructure and dense populations. Seasonal timing also matters. Spring is a season of contrast by nature. Warmth is advancing, cold air still remains available, and the jet stream often remains active enough to organize major systems. This makes spring a natural season for conflict between air masses. In a changing climate, that seasonal conflict may not disappear. Instead, the thermodynamic side of it may be altered. Moisture availability may increase. Early warmth may arrive sooner in some years. Some transition zones may shift. But the exact effect on the most violent storm outcomes remains an area where scientific caution is necessary. Observations indicate change in several supporting ingredients. It remains uncertain how those changes combine place by place and storm by storm to affect the rarest and most violent tornadoes. That uncertainty is not a weakness in the science. It is a reflection of the atmosphere's complexity and of the care required when connecting long-term climate signals to short-lived severe events. Still, even uncertainty has shape. It does not mean nothing is known. It means some parts of the chain are firmer than others. The moisture side is firmer. Heavy rainfall risk is firmer. The broader reality that a warmer atmosphere changes the background conditions in which severe storms develop is firm. The precise evolution of tornado frequency, intensity, and location is less firm and remains under active study. Returning to the outbreak itself, the deepest lesson is not that one storm proves everything. It is that one storm reveals how many layers of the atmosphere can align to produce several kinds of danger at once, and how those alignments occur within a larger climate system that is no longer static. The continent still breathes in, seasons still exchanges warmth, and cold still lifts moisture into cloud and rain and ice. But the background state of that breathing is changing. Some signals are already clear, some are still emerging, and the weather of spring now unfolds inside that unfinished scientific story, where what is established and what is uncertain must be held together with the same care that meteorologists use when reading the sky itself. The atmosphere finally begins to ease. The great circulation that stretches across the continent does not vanish all at once, but its sharpest edges soften. The fronts move on. The strongest updrafts weaken. The violent contrast between warm and cold begins to lose its grip. In the wake of the storms, the land remains marked by what has passed through it. Water settles into rivers and low ground. Broken branches lie still. Meltwater drips from ice where the colder air had held its place. In some regions, the sky clears by degrees, and in others, low clouds linger a little longer, as though the atmosphere itself is slow to release the tension it carried. What remains most striking is the unity behind the seeming disorder. Tornadoes, floodwater, hail, freezing rain, blizzard, snow, and record warmth appear at first like separate stories, but they belong to one broad atmospheric design. Warm, moist air rises where it is lifted. Cold, dense air settles and advances where the circulation allows it. Wind changes with height and gives storms their structure. Boundaries divide one air mass from another, and along those boundaries, the sky decides what form its energy will take. The continent becomes, for a brief time, a place where several seasons exist, together, each one pressed against the next. The storms move on, but the pattern they reveal remains worth remembering. The atmosphere is never random in the deepest sense. It is fluid, layered, and governed by physical rules that turn contrast into motion and motion into weather. Some parts of that process are well understood. Some remain difficult to resolve in full detail. Yet, even in uncertainty, the larger picture holds. A storm outbreak is not only a spectacle of danger, it is a display of how air-water temperature and motion join across enormous distances and then descend into local consequence. By the end, the sky becomes quieter than it was before, not because its forces were small, but because they have already spent themselves. The rain lightens, the wind becomes ordinary again. The land begins the slow work of absorbing what the atmosphere has done.